Welcome to this video on applying Ampere's law to a solenoid. In this video, we're going to take a look at employing Ampere's law, how to set it up, and then how to actually make the calculations. This will also be an extension of the solenoid video that we have had before, where you were taking a look at how visually the magnetic field superpositions to create a net magnetic field inside a solenoid. So if you haven't checked that one out, you want to go ahead and check it out, and then also take a look at the Ampere's law introduction video as it compares it to Gauss's law, which is very helpful. So the first thing is that we're looking at a cross section of the solenoid. So this would be the solenoid, a half of it, like cut down lengthways. And so if you're looking at just one of these loops from the side, you would see this curve that looks something like this. The current is going into the page at the top and coming out at the bottom, and so on and so forth. So if I used the what I call the third right-hand rule, where my fingers go in the direction of the current, then my thumb should point to the left, meaning that the net magnetic field is pointing to the left. So I'll go ahead and put that in here. The net magnetic field is pointing in this direction. Now, of course, it's continuous, but because of the superpositioning, what's happened is that any vertical components between each of these coils have canceled out, and all of these horizontal components have added together to make a magnetic field pointing north in this direction. Now, what we're going to do is follow these basic rules. So if you want to screenshot this, that you have maybe a little cheat sheet on how to set it up. The first thing is we want to identify a point in question. Now, what are we even talking about? Well, Ampere's law is oftentimes used to figure out a value for magnetic field, so a value for B. And what I want to do in this video is take a look at how do we figure out what the B value is, the magnetic field is inside the solenoid. Because one of the cool things about a solenoid acting as an electromagnet is that I could put a permanent magnet or another solenoid over here, and depending on the direction of the current that I have running through this, I can either attract the solenoid or repel the solenoid from whatever else is over here. And the amount of attraction or repulsion will be based on how strong the magnetic field is that I have inside here. So that's what we're going to do. We're going to try to figure out what is the magnetic field at this point. So some of the ways that we might go about doing that. We've identified the point in question, so we want to know what is B over here. Now we're going to identify some other points in the vicinity of the same point that should have the same magnetic field. So using the ideas of the fact that the distance is the same on all sides here, these several points maybe that I'm making, they should all approximately have the same magnetic field. Now before I forget, I want to just keep in mind that we're not looking at the edges here as much, we're just kind of looking at the interior of this. But it works out to actually be a very good approximation of a solenoid magnetic field. Specifically one that has an iron core in it, because you can put different rods with different cores into them to help with the magnetic field. Now we're going to draw a line that connects these points. So I'm going to go ahead and just connect the points that I already have shown over there. So I'll go ahead and draw this across like that. The next thing is to decide on a closed loop or a closed path that encloses some or all of the current that is creating the magnetic field. So this is the part where we have to think and be a little creative in how we decide to draw the magnetic field. So jumping back to Gauss's law here for a second, if we had a line of, let's say, a positive charge, and we were trying to figure out what the electric field was at this point over here, what we decided to do was, one of the things we would do is we kind of follow the same first few steps, and we'd say, let's find some other points where the electric field would be the same. We'll connect those points. Now we'll go to another place around the shape where it would be the same electric field, so over here. And then we would think, okay, well, what closed surface could I construct around this that would have either some surfaces of the closed shape have no electric field, and some surfaces of the closed shape have a constant or the same magnetic field. So here's what I mean. if I were to pick to draw a cylinder like this, so we could do it on all sides like this, we would say that the electric field from the positively charged conducting rod would be pointing in this direction. So we can see that we have a net amount of electric flux through all the sides of this. So if you think of it as like a toilet roll or something, through all the sides of that we have some flux. Through the top, however, and the bottom, the flux on those portions is zero. So I've constructed a shape here where I don't necessarily have the same electric flux through all surfaces, but the surfaces that do have flux, it's an equivalent amount. Okay, so it doesn't change. We want it to be an equal amount of electric field. The top and the bottom obviously have no flux. So what I've done here is if I was going to add up all the flux portions in order to use Gauss's law for electricity, I would have here that this E is constant, so it can be pulled out of the integral, and then I can just add up all the area portions. I don't have to add the top and the bottom because of the shape that I've selected. Now if I selected a different kind of shape, like for instance if I turned this cylinder on its side like this, that wouldn't be a great idea because I might have something that's a little bit more difficult, but in this case it might actually work. So you can use multiple shapes, and the same thing is going to be true for the Amperian loop that we're about to draw. So instead of drawing a surface, we're going to draw just a loop or a path. So according to the law, Ampere's law, we have this path integral or line integral B dot dl is equal to mu naught times the current that is enclosed by the loop. Much the same as Gauss's law, we have the charge enclosed. So what we're going to do here is we remember that this is a dot product as well. So we're going to try to draw a shape that maybe through some sides of the shape there will be a constant amount of magnetic field. Through other parts of the shape maybe there's no magnetic field. So I'm going to go ahead and do that. I'll draw this line along here, and I'm going to turn up this way because I have to enclose some current in order for this not to be zero. Otherwise I'm picking a shape that's not going to help me figure anything out. Now I'm going to explain to you what the heck I'm doing here in a second, but let me make this a very long rectangle, and we'll join it over here. I'll label the edges or the corners so that we can explain what's happening. We are looking at how the magnetic field lies along the little pieces of the loop. Okay, and if we add all those magnetic field loop pieces, we should get the total amount around this specific space that we've drawn. So basically what we're going to say is we're going to look for the quantity B dot dl, or B times delta L, for the segment, let's start here, A to B, then for the segment B to C, for the segment C to D, and then finally D back to A. So this would be like the sides of the cylinder and then the top and the bottom of the cylinder when we were talking about Gauss's law. So we're just doing it all piece by piece, and essentially what we're going to do here is add up all the pieces so that we can get this side of the equation. So from A to B, we know that our magnetic field vectors or our magnetic field vector is pointing this direction, so that's B, but the DL vectors are pointing like this, right? So they're at 90 degrees to each other, especially just in this region. And so we see that if this is a dot product, we're looking at B dl cosine of the angle between B and dl, and if that angle is 90 degrees, then the cosine of that 90 degrees is equal to 0. And so along A to B, there is no portion that we have to add. So from A to B, we know that this is going to be equal to 0. From B to C, this is just really so far away that there is no magnetic field at this point. And even outside here, we would have canceled out the majority of the magnetic field due to each side's contribution. But definitely out far away here, B to C is 0. So we're going to have that be 0. C to D is going to be 0 for the same reason that A to B was, because down here, wherever it does overlap, we still have that cosine of 90 degrees, so that's 0. And so we're left here with D to A, where we're going to add up the magnetic field. Now think about it, the green arrow, the big green arrow, represents the direction of the magnetic field, and the direction of the DL vector is in the same orientation. So here, the BDL cosine theta, in that portion, theta is equal to 0 degrees, and that I know the cosine of 0 degrees is equal to 1, and so I know that I have their value of BDL times 1. So if I sum up now, if I do the summation of all the little DL vectors times B, what I'm going to essentially get is B times L. Now that would be me calling the length D to A a value of L, but you could call it something else like X or whatever you want to call it. So we have B times L. So what I've done here is I've essentially found each segment's contribution to this dot product. Okay, now I can set it equal to what's over here on the right. So we have B times L equals mu naught times I enclosed. Now, based on what I did here, if you think about it, if we had a constant current running through this solenoid, going in through the top, out through the bottom, in through the top, and so on and so forth, we have a set amount of current. Let's say it's 12 amps. Well, I'm enclosing 3 of these overlaps, right? And the fact that the magnetic field here is created from multiple superpositioning, so like lots and lots of overlaps of the magnetic field, is why the solenoid is pretty powerful, because it has a very overlapped, strong magnetic field due to the multiple overlaps of the current. So over here, I don't just have 12 amps flowing through this Amperian loop, and I should write that out so that you can remember that term. That's analogous to the Gaussian surface. The fact that I have 3 of those segments running through my Amperian loop means I have to do n times 3, or n equals 3, so n times the current to get the actual amount that I am showing in this particular segment. So that's n times the I value that's enclosed. Now, I picked 3. You could have picked 4, 5, 6, 7, 8, 9, 10, and it would have varied. But because it's proportional to L, the length of this, the number of loops that I enclosed relates to the length of this. So right now this might be a 3-turn solenoid that has a length of L, but I could stretch this out, and so N can become pretty much any number. So if we solve for B here, we get this is equal to mu naught times N times I over L. This would tell me the magnetic field strength at a position along this center point. Now, what we usually do with a solenoid is, instead of putting N over L, what we do is use a lowercase n, and we say that that is equal to the number of turns per unit length. So we have number of turns per unit length is little n, so I can instead write this equation as B is equal to mu naught times N times I. And if you do it this way, then you have something that's flexible for any stretch of a solenoid. So here we have an expression for the magnetic field. You could use either one of these, the magnetic field inside a solenoid, using Ampere's law in order to do that. So it's a very useful tool. We will look at 1 or 2 other examples of this in another video, and then take a look at a few other examples using the Biot-Savart law, so you can see when it's a good idea to use Ampere's law versus when it's a good idea to use the Biot-Savart law, or when you can only use the Biot-Savart law.